the shortest of the sections in the notes, which is section 3.8, so that's page 78. So, to remind you, for certain choices of generalized linear model distribution, there's an extra parameter phi which you need to estimate. So this is on top of the parameters that you need to estimate as part of the linear predictor, and it's called a scale parameter or dispersion parameter, and it's essentially analogous to the variance parameter which you need to estimate in a ordinary linear model with the normal distribution. For the binomial and Poisson, the form of the distribution tells you that this value is 1. So if you're doing a standard binomial or Poisson generalized linear model, then you don't need to estimate phi. But if you're using one of the distributions like the gamma distribution, where you do need to estimate phi, we should think about how you estimate it. So common practice is to observe that we have two quantities which we've defined for generalized linear models, both of which have approximately chi-squared distributions with n minus p degrees of freedom. One of them is the Pearson chi-squared statistic, and one of them is the deviance, the residual deviance. Okay, so both of those, if you scale them by phi, give you something which has a chi-squared distribution with n minus p degrees of freedom. Now, a chi-squared distribution with n minus p degrees of freedom has mean given by n minus p. So if we want to estimate phi, then we can take either the Pearson chi-squared statistic, which is the one given here, or the residual deviance, and we can divide by n minus p. So that should give us something which would have mean given by phi. Okay, because if we divide by phi, we then should have something as well as dividing by n minus p, which should have something with mean 1. So we've divided by both the n minus p, which is the mean of the chi-squared, and the phi, which scales us to the chi-squared. So just dividing by n minus p should give us an estimate of phi, should give us something which has mean phi. So we can use either the Pearson chi-squared, the system is being slow to actually get going on my, here we are, right, there we are, or we can use the deviance, residual deviance, for the fitted model. Again, in both cases, we can divide by n minus p. Okay, so n minus p here is the usual number of degrees of freedom, the number of observations n minus the number of parameters that we've fitted in the model. Okay, so the parameters here excludes phi, so it's the number of terms in the linear predictor, including the intercept. So it's just the usual number of degrees of freedom for either a linear model or a generalized linear model. Okay, now in R, you'll see if you fit one of these models that there's an estimate given. It says what the dispersion parameter is for your model in your R output. Most of the examples we've seen have been binomial or Poisson, so it then just says 1. But if you use a gamma, for example, it will give you this. So it uses the chi-squared estimate. I think that's because the chi-squared statistic is closer to having the chi-squared distributional approximation is better for the chi-squared statistic than it is for the residual deviance in certain situations. I think that's why R prefers to use the version with the chi-squared. Okay, so this isn't a maximum likelihood estimate. It's comparable to the situation in the usual linear model theory for the normal distribution, when you're trying to estimate sigma squared, the variance. There's a maximum likelihood estimate of sigma squared, and there's an unbiased estimate of sigma squared, where you take the residual sum of squares and divide by n minus p. And both of these things are very similar to doing that. They're basically generalizations of doing that, because both the Pearson chi-squared and the residual deviance are generalizations of the residual sum of squares to generalized linear models. Okay, so what we're doing here is similar to what we did in the normal linear model, but it's not a maximum likelihood estimate. It's instead designed to be an unbiased estimate. And at the top where it says moment estimate, basically a moment estimate is one which is designed to be unbiased, because it means that we're trying to get the moment, particularly the mean, right. Okay, so that was as I say, the shortest section in the notes. So, as I said on mole, I'm now going to do chapter 5 before chapter 4, and that's because chapter 5 is going to be useful to the people doing the MAS6003 where the project involves the Poisson. So chapter 5, this starts on page 86 in the printed notes. So chapter 5 is about Poisson regression. So we've actually already seen examples of binomial regression. Okay, so like the Beetle data, there we assumed that we had an underlying binomial distribution. Where we have things which are counts, and unlike in the binomial distribution, we don't have some fixed number of trials that we're counting successors in. The Poisson distribution is often a good starting point as a model. So in particular, if you have events occurring randomly in time, so things like accidents, telephone calls, deaths from a particular rare disease or anything like that, so things which are particular events occurring in time, the Poisson distribution is often a good model for that sort of data. And we will see a couple of examples, hopefully I'll get to them today, where we use Poisson regression for data which is of that sort of type. Okay, so the Poisson process is a probabilistic model, which some of you may have seen. And if you haven't seen it, in the appendix on mole, I put a little bit about the Poisson process, so you can read about it there. But essentially, the fact that the Poisson process is a useful model for this sort of thing, where events are occurring randomly in time, means that the number of events which occur in a particular time interval would have a Poisson distribution if you assume a Poisson process model. Okay, so if we're modelling counts of some sort of event, particularly in time, then it often makes sense to use the Poisson distribution as a model for them. Okay, so in the last chapter, which as I've said I'm probably not going to be able to say very much about in the lectures, we'll see that there's a further connection to contingency tables. So it turns out that you can essentially treat contingency table data as Poisson. Okay, so Poisson generalized linear model. So we've got count data. So count data are, by their nature, they take non-negative integer values. Okay, now the mean of a Poisson distribution is the parameter mu I. So if we assume that our random variables yi have Poisson distributions with mean mu I, then mu I is the mean. So we're going to want to think of the mean, mu I, as being equal to our inverse link function h of our linear predictor. So remember the linear predictor, which we've written as eta I, which is also equal to xi transpose times beta. That is what we actually get as our linear combination of the regressor variables weighted by the coefficients. So we're going to apply the inverse link function h. That will give us mu I, which is going to be the parameter, and hence the mean, of our Poisson distribution. Okay, so what link are we going to use? Well, we've already seen the idea of a canonical link function, and in the notes there, one of the tasks, there was the opportunity to calculate the canonical link function for various distributions, including the Poisson. And if you do that, you see that the canonical link function of the Poisson is the log link. Okay, so that means that the link function g is the log, which means the natural logarithm here. So that means that the inverse link function, which is h in that line at the top, is the exponential function. So the mean, mu I, is actually the exponential of xi transpose times beta. Okay, so if you think about what that means, xi transpose times beta is actually going to be a sum of some things. So it's going to be something like beta naught plus beta 1 x1i plus beta 2 x2i, or something like that. Now if we're taking exponentials of this, so exponential of xi transpose beta, which is what we do if we have a log link, then this is the exponential of beta 0 times the exponential of beta 1 times x1i times the exponential of the beta 2 term. Okay? So when you have an additive structure for your linear predictor and you apply an exponential function to it, you get a product of the exponentials of the individual terms. Okay? Just to be consistent with the notation on the screen there, I'll have the i's and j's the other way around. I1 and I2 there. And up there as well. Okay, so that means that the log link has this very natural representation as a multiplicative thing. Okay, so we have a multiplicative structure that mu I is a product of terms corresponding to the individual regressive variables. So it's a product of the exponential of the regressive variable times the coefficient for each term. Okay, so in some sorts of models you might have, say, a term for age, and now because it's a multiplicative structure with this link, you would be multiplying by a term for height. Okay. One thing that you can do if you want to check whether a link function is good is that you can plot the value of your link of your data values against excuse me, against your if you just have one variable xi, you can plot the value of your link applied to your observed values against your single explanatory variable xi. Okay, now our link function here is log of yi, so we would plot log of yi against xi. Now if we were going to have a good model, so we didn't need something like a quadratic term or a log term or any extra parameters, then we should get approximately a straight line. Now there's a problem with doing that, which is that if your count is 0, which sometimes it might be, you might have no events occurring in a particular time interval, something like that, then log of 0 is undefined or goes off to minus infinity, however you want to think about it. So we need a correction, And a natural correction is just to add on a small amount to the observed values before you take logs. And a convention is to add on a half. So instead of plotting the logs of the observed values against xi, plot the logs of the observed values plus a half against xi. So that avoids problems if some of your observed values are equal to 0. You can use other links, but there aren't, unlike for the binomial, there aren't so many built into R. So the log link really is the default link to use with the Poisson distribution. Okay. We can calculate formulae for the residual deviance and the Pearson residuals and the Pearson chi-squared. In fact, we've already seen a formula for the residual deviance back a few pages ago, and it looks like this. It actually usually simplifies a bit. So if we have a constant term, and we've got the sum of the yi's minus the fitted values, that's usually 0. The sum of fitted means is usually equal to the sum of the observed values. So the sum of if you take the yi minus mu hat I and you sum them all up, you normally get 0. So if you have an expression summing yi minus mu hat I in an expression for the deviance, that's usually 0. So in fact, usually we can simplify this to twice the sum of yi times the log of yi over mu hat I. And sometimes, this particularly arises in connection with contingency tables, people use the notation O to mean observed values and E to mean expected values. You may have seen that before. Now the observed value here is the yi, and the expected value is the mu hat I under the model. So we're actually summing twice the observed times the log of observed minus expected. Now if observeds are usually close to expecteds, then this will be close to 1. And if something is close to 1, then its log is close to 0. So we would expect, so if the observeds and expecteds are usually close together, we would get a small value for the deviance. Okay, the Pearson residual, so this is actually just from the standard formula for a Pearson residual, except that the Pearson residual has a term root wi in it. The root wi for the Poisson distribution is 1. So those wi, those weights, come in for the binomial distribution, but for the Poisson or the gamma or the normal, they're generally 1, so you don't need to worry about them. And the variance function, which appeared in the denominator for the Poisson, the variance function, the v of mu I, is equal to mu I, because the variance of a Poisson is equal to its mean. So where we had the square root of the variance function in the denominator here, we now just have the square root of the estimated mean. So we have yi, the observed value, minus mu I hat, the fitted value, divided by the square root of the fitted value. So that's the Pearson residual in a Poisson model. Okay, so yesterday I defined the Pearson chi-square statistic, which I also mentioned at the beginning, as being the sum of the squares of the Pearson residuals. So if we square those things on the top line and add them all up, we get the sum from I equals 1 to n of the squares of the differences between between the observed and expected, and we divide again by our fitted values. Now without the square root because we've squared. Okay, so x squared here is the sum the chi-squared, Pearson chi-squared statistic, is the sum of these squares of observed minus expected divided by the expected. Now, if you've seen chi-squared tests for goodness of fit in your previous statistical studies, then summing up observed minus expected squared divided by expected is exactly what you do if you're summing, if you're doing a Pearson chi-squared test for goodness of fit. So there are some similarities for the formulae that we get for the Pearson chi-squared statistics for Poisson regression, and as we'll see also binomial regression, to test statistics for tests that you may have seen before involving the chi-squared distribution. Okay, so Poisson regression is, as we've seen from actually getting the form of the distribution in the right form in chapter 3, it's a generalized linear model, and the variance function, as I mentioned, is equal to mu. So the variance of a Poisson is equal to its mean. The extra parameters, the dispersion parameter phi is 1, and the weights are 1 as well. So there's no extra contribution coming from the dispersion parameter or the weights for a Poisson. So it's actually really one of the simplest types of generalized linear model, because those are both known to be 1. Okay, so we can do almost everything as we've seen in chapter 3. Phi is 1, so the residual deviance is asymptotically something which has a chi-squared distribution with n minus p degrees of freedom. Now, what do we mean by asymptotically here? Well, we need a reasonably big data set. We also need the Poisson parameters to be large enough that a normal approximation is reasonable to the Poisson distributions themselves. If the Poisson parameters are small, then the chi-squared distribution may not be a particularly good approximation. The document that I put on Mole simulating binomial and Poisson values and looking at the distribution of the deviance, it's mostly about the binomial, but it does say a bit about the Poisson as well, and if you look at that you'll see roughly how far out the deviance can be. So if the mu i's are fairly large, so those are the Poisson parameters, then it's a good approximation, but if they're quite small, then beware. Be a bit careful. Okay, so let's do an example of some actual Poisson regression. So here's some data which are deaths from AIDS in the 1980s in Australia. So this is example 38, age 87. So the format of this data is a little bit strange. The deaths are per quarter. So we're divided each year into quarters, and the labelling of the x variables, which are the quarters, so that's our periods of time, is such they're in order. So quarter 1 is the first quarter of 1983, quarter 2 is the second quarter of 1983, so continuing with that, quarter 12 is the last quarter of 1985. There are 14 quarters in the data, so the quarter 14, the last one, is the second quarter of 1986. So it's from 1983 through to the middle of 1986. Okay, so we have the number of deaths from AIDS in Australia in each of those quarters. And I haven't put the full data on the slides, but if you look in the notes, you've got the full data. You can see that they tend to increase over time. So in quarter 1, in fact, there were none, but then the numbers were quite high in the later quarters. Okay, so here are some plots. plots in the notes as well as figure 5.1. So the plot on the left is the raw data, so the deaths per each quarter, and you can see the increasing trend in that plot. It's a little bit irregular, so there's a dip there and there's a dip near the end as well. Just move the mouse pointer out of the way so it's not getting in the way of that first plot. So that's showing the trend. However, to look at the validity of a log link and with a properly linear predictor, as we've said, we want to plot the log of the number of deaths with that small adjustment of adding a half to avoid the problem if one of the observations is 0, which in fact it is here. So this is what we get, and it looks reasonably like a straight line in this plot on the right. You might think that it looks like it's dipping a little bit towards the end, so it might not be that good a fit on a straight line, but it looks reasonable, and if it is dipping, that could just be an artifact of the last two being unexpectedly small. So I think it looks like a reasonable fit there. Okay, so the left plot there just showed the data. The right-hand plot there, as I said, showed the logs of the data plus a half against the quarter number. And as I say, there's perhaps a hint of downwards curvature, but the straight line looks reasonable. Okay, so we're going to fit a Poisson regression model to that data set. And because we're using a log link here, this was, as the default for Poisson, this was the right thing to look at. Okay, so what happens if we do that? Well, the null deviance is pretty large. So remember, the null deviance is what we get if we just assume a constant term in our linear predictor. So we would have the same mean, the same parameter for our Poisson distribution, counting the number of deaths, in every quarter in that data. Now, if you look back at the picture, that's a most implausible assumption. It definitely looks like there's an increasing trend over time in that data set. It's not surprising at all. The null deviance is large. There are 13 degrees of freedom because there are 14 quarters. We've estimated one parameter, the constant term, so 13 degrees of freedom. 207.272 is a seriously large value for a chi-squared 13. Even if you're a little bit worried about the chi-squared approximation to the deviance distribution, it's not out by that much. 207 is a seriously big value for a chi-squared 13. Okay, so what happens if we use a linear predictor, so beta 0 plus beta 1 xi. So xi, remember, is the quarter number. Beta 0 would then just be the constant term. So this would fit an increasing trend which had a linear term, which we then take the exponential of. So it would say that mu I, the mean for a quarter, was exponential of that constant plus beta 1 times the quarter number. So it would suggest a linear increase in time of something which we then take the exponential of. Okay, so if we do that, we get a residual deviance, which is a lot smaller than the one we had at the top. We've fitted an extra parameter now, the beta 1. So we now have 12 degrees of freedom. And we get 29.654. That's still a little bit large. So if you test that against a chi-squared distribution with 12 degrees of freedom, this gives you the p-value. The 1 minus is because we want the upper tail. And you get 0.0032. So that's a fairly small p-value. Again, you might be a little bit worried about how good a fit the deviance is to a chi-squared distribution here, but I think this value is small enough that we do have evidence of a poor fit, even with that caveat. So we might want to think about how we improve this fit. So one thing that we can do is we can add a quadratic term. So we've seen earlier in the course that this is often a trick which we can use if we think we have a poor fit. We can try and improve it by adding a quadratic term. Okay, so what happens if we do that? Well, we've added an extra parameter, so we now have 11 degrees of freedom, and the residual deviance reduces to 16.371. The mean of a chi-squared with 11 degrees of freedom is 11. So this perhaps still looks a little bit large, but it's not too bad. The p-value we'd get if we assumed that we really did have a chi-squared model for our residual deviance would be 0.13, so it's not generally regarded as significant. So there's no real evidence of a problem, and if we use the test based on residual deviances, difference in residual deviances, sorry, for comparing the model with a quadratic term and the one without, we find there's strong evidence to reject the null hypothesis that the quadratic term is 0. So adding the quadratic term has given us what looks like a reasonable fit to the data. It turns out that if you use a log term instead, so this is actually getting rid of the xi entirely and just using log of xi on its own. Okay, so that's another way of fitting something which is curved before applying the link function. So if you do that, so your linear predictor e to I is beta 0 plus beta 1 times the log of the xi's. Okay, so that would mean that the Poisson parameter was the exponential of that. Then that does better, in fact. So fitting to the log of the xi's does better than fitting to the xi's themselves. So we now still have 12 degrees of freedom because we only have got the two parameters there, the constant term and the coefficient of log. And the residual deviance is 17. So that's actually fairly similar to what we got with the three parameters in the original model. That's also a possible model, and it seems to be about as good as the quadratic one. And if we try and add a quadratic term in now, so this is now a quadratic term in the log, so log of xi squared would be appearing, that doesn't help us. It does reduce the deviance a little bit, but just like r squared for the ordinary linear model always increases, the deviance always decreases if you add in an extra term. You always improve the fit if you try and fit an extra term. So this decrease in the deviance is distinctly unimpressive. Remember that the 0.95 quantile of chi-squared 1 is, I think it's 3.84. So we'd want to be reducing the deviance by around 3.84 at least to be having evidence that the model's better. So going from 17.09 to 16.64 is not impressive. So there's no reason to include a quadratic term in the log. So there are a couple of models that look reasonably plausible from this. So just a simple linear predictor, but with log x's, or we could have a quadratic, so with a constant times x plus another constant times x squared. So there are there are a couple of possibilities there. You might find that a different choice of link function would give a better fit. Okay. So there's a particular feature of a Poisson model which does actually occur in some, can be used in some other context as well. It's particularly relevant in a Poisson model. So imagine that instead of quarters in the last data set, some of the lengths of time, instead of being quarters, were years. And let's assume that there was no underlying change in the rate of deaths due to AIDS in Australia over the period. Okay, so that clearly wasn't the case, but imagine that it was. So you have some lengths of time which are quarters and some lengths of time which are years, and that there's no underlying change in the rate of things happening over the period of interest. Now in that case, the number that we might expect in a year would naturally be 4 times what we would expect in a quarter. If we have the same rate of things happening in a quarter as we do in a year per unit of time, then the overall parameter that we get for the Poisson distribution in the year would be 4 times larger than it would be in the quarter. So if some of our periods were quarters and some of our periods were years, we would expect to have Poisson parameters which were 4 times larger for the years than for the quarters, even if there was no change in the underlying process. Okay, so let's generalize that idea a little bit. Let's say that yi are numbers of events, and they're in some time periods, and those time periods now have lengths which, unlike in the Australian AIDS data, are allowed to be different. So period I now has length ti. Okay. So if we do a model with a Poisson process, and we have an underlying rate of the Poisson process as being lambda I in the ith interval, then the Poisson distribution, the Poisson random variable, which counts the number of events in that period, wouldn't have the unmodified parameter lambda I, it would be multiplied by the length of time. So you multiply the underlying parameter of the Poisson process, lambda I, by the length of time ti, and that gives you the parameter of the Poisson distribution for the number of events occurring in that time period. So we multiply the Poisson parameter by the length of the interval to get the actual parameter that we're going to use for the Poisson distribution. So mu I, the mean of the number of events that occur in that time interval I, should be the underlying rate in that interval, lambda I, multiplied by the length of the interval ti. Okay, so let's now take logs, which gives us our linear predictor because we're using a log link. So the original linear predictor would have been xi transpose beta. Now, what we're really likely to be interested in are these underlying rates. The lengths of time that appear in the data collection, those being different, is an artifact of the data. It's essentially a bit of an annoyance. But sometimes it's unavoidable, as we'll see. So if we do that, we can model the lambda I, the underlying rates of the process, by our usual linear predictor, xi transpose beta. And now because we've taken logs and we were multiplying by ti, we add on the log of ti. So the log of mu I should instead now be what the original linear predictor was, plus the log of the lengths of the intervals ti. Okay. So the log of ti here looks like an extra regressor variable. Okay, we have an original regressive variable which looks something like this, and we're now adding on the log of the TIs. Now that's fine as far as the x's are concerned. We can just say that xi3 is the log of TI. However, we would then have beta 3 here, and we know what that should be. We know that it should be 1. Okay, so we actually want something which looks like an extra regressive variable, but with a coefficient which is known to be 1. Okay, so this is the natural thing to do if the lengths of intervals are varying. Okay. Now, there are ways, as we'll see in a minute, in fact, that don't actually look naturally in terms of lengths of intervals, that also affect the amount of exposure to the events happening. And we can treat those in the same way. So we add on the log of the exposure in that interval as an extra regressive variable, but with a known coefficient, which is 1. Okay, so now what we're doing is we're looking at the rates per unit exposure rather than the overall rates for the observation in question. Okay, so we could have, for example, death counts of some disease, and you have in the same time period, but over different populations. So the larger populations, you would expect to have a larger parameter for the Poisson process, regardless of the actual underlying rate of the disease there. Larger population would give a larger death rate. So the exposure there would be given by the population size rather than the time, as it was in the previous example. So this quite often occurs with Poisson data. Okay, so now our offset would be the logarithm of the population size. Okay, so there's a function which you can include in a linear model term in R. So it says here that you can use it as an offset for a Poisson regression model. You can actually do this for any linear model or generalized linear model. You can add in an offset, which is an extra regressive variable with known parameter. Some of you actually did this in exercises 2 with an ordinary linear model where you were testing for a parameter being equal to a particular value. And it works as a way of testing that. Okay, so we use this offset in R. And you'll see an example of some code later. So here's an example of something with an offset. So this is a famous data set. This is death rates from coronary heart disease, and it was over 10-year periods, and they were looking at the data set, curiously, was actually doctors, and the data is to do with whether the doctors were smokers or not. Okay, so this is some of the original data which convinced the world that smoking was dangerous. So in the data that you on the page 88 of the notes, the age groups are numbered. So this gives what those mean. So age group 1 is 35 to 44, age group 2 45 to 54, and so on. Okay. So we need to know the exposure. So if we're looking at deaths, we're counting the deaths due to coronary heart disease in this data set. So let's say that we're looking over a 10-year period. What we want is the number of people multiplied by the number of years, with the correction that if somebody disappears in the data set, either because they died or they weren't available anymore for whatever reason, and it could have been, they could have died of the thing of interest or of something else, they're no longer exposed. So we would correct for that by just adding up person years. And now you can see, I mean, the number of doctors in the 75 to 84 age group is likely to be rather less than in some of these age groups in the middle. So you would expect that you would have fewer deaths in this just because you have less exposure. You have fewer people in that age group. Okay, so here's the data. So we have the number of person years for each age group, and we see that among smokers we do indeed have fewer deaths in age group 5, even though they're older, than we do in age group 3, but there's massively more exposure in age group 3. Okay, so what we do in fitting this, we actually convert those age group codes to the midpoint. So that gives us an estimate for the doctor's age. Okay, so 40, for example, for that youngest group, and 80 for the oldest. So if we look at death rate, so these now deaths per person year, we get these figures, which are increasing over time, as we would expect. And we note that they are mostly higher for the smokers than they are for the non-smokers. There's actually an exception for the oldest age group where the one for non-smokers is slightly higher. Okay. So if we plot log of death rate against age, we see that there are differences. So we will see these plots in a minute between the two groups. And furthermore, there's some curviness in the data which suggests that a straight line isn't going to be a good model. So let me actually scroll through to those plots. Here we are. So the top right one is the one that I'm talking about here. So the top right has the log of the death rate plotted against age. So the squares, which are the higher ones, are the ones for smokers. The triangles are the ones for non-smokers. And you can see that that doesn't really look like a straight line. It looks like they're increasing with age, but at a rate which slows over age. So that might suggest that we want to, say, fit a quadratic